So I'm going to get started. First, I will mention a few things, make a few plugs. So I actually kind of expected maybe the majority of the room to be computer science undergrads, but that's maybe not the case. Like, raise your hand if you're not a computer science major. Almost nobody as well. Okay, so much for my statistical reasoning. I wanted to make like a plug for sociology, especially for kind of computational people. Really, there's like huge space, I think, to be filled there. And obviously, computational social science in general, and I imagine a lot of you are in that, either in that space or trying to get into it. It's exciting. So one of places through which to do it is our knowledge lab. We have a lot of exciting projects. If you go on the website, there's like a billion of them or so. And it's anything from predicting which scientists will collaborate to what science is cited on Wikipedia to how knowledge travels from poetry to the scientific literature. I mean, I'm thinking of science because that's sort of my space, but it's kind of general knowledge. So it's kind of hard to describe, but that's what we try to, tackle. The other thing I wanted to mention is data science for social good. So these are the two things through which I sort of got exposure to these tools and stuff. DSSG, raise your hand if you, I guess, have heard of DSSG. Not definitely be some of you, but not too many. So it's a summer program. It's now actually a full year center, but it's this specifically is a summer program. It's funded by like Google's ex-CEO Eric Schmidt, and it's for people who are interested in kind of computational techniques to do kind of a consulting project with like a nonprofit for the summer. And so there are teams of sort of 3 or 4 people, and you work for really cool organizations like the World Bank. What else? Energy utilities, the country of Jamaica, et cetera, et cetera. It's like pretty cool. The deadline to apply for that is like really soon, like a week-ish or so. So, if you haven't done it, if that hasn't been on your radar, now it's there. Another raising hand exercise. Who was not able to get set up with iPython notebook and running all that stuff? So at least, okay, we got a couple of people. Okay, more than a couple. So the rest of you are up and running. Everything's fine, sounds like. I imagine, yeah. Those of you who couldn't get it going, there's this website, wakari.io, which will give you a virtual environment. I think you just have to like make a little account. I think it's pretty painless, and it'll have all the tools we're going to be using. So I'll also mention that we will have a couple of TAs, assistants, in the room. So Bill is one of them. Bill can raise his hand nice and high. Another stylish fella. And then Nathan is coming in at 5:30 or so, and he'll also help out. And also interrupt me at any point with whatever issues, questions. All right, so let's talk a little bit about the notebook environment. So I have no idea what people use generally. I personally came from a whole bunch of things to using I think Spider was my IDE, integrated development environment. Like that's where I did my coding, and now I've switched completely over to Notebook, which I totally hated at first. But so if it's your first IDE, that's fantastic. If not, I'll sort of mention some advantages, disadvantages. So the reason it's really, really cool, probably like the number one, at least to me, like obvious benefit, is that here, in addition to all my tabs, which I should have hidden, just in my browser, like we have this huge page which has some images and code, and it's so interspersed, and that feels like a notebook, right? Like you're sort of like scrapbooking, like you're putting images wherever you want, you're putting text, you're putting links. That's really unusual and fantastic, I think. So like that as a social scientist, to me, that feels very intuitive and nice because I can have my analysis results. That's, I think, an awesome feature which we didn't get before with the usual IDEs. So the text you see here is Markdown, which is kind of like scaled down HTML type of thing. So each cell within iPython, so I hit my toolbar, but you can have different types, and that these will be like different font sizes, code, and this Markdown language, and so that allows you to really kind of format things nicely. You can run this on a server and just sort of view it, in your browser. That's also a really nice feature. That's how I do all my work these days. I have my stuff running somewhere, and then I just gotta work on it from my browser. That's cool. Lastly, keyboard shortcuts are pretty crucial. So without these, I think it's pretty much like so annoying. It's like you have to click. Like if you want to run a specific cell, you have to like get your little cursor like over here and click. That's annoying. So you pretty much have to learn the keyboard shortcuts. So you can go to Help and click here, and it'll pop up a menu. Cool. So there's what 50 things here. I've memorized like 10, because you basically can't work without using these. It's just you pretty much like Control Enter runs the cell that executes the code in the cell. Then I guess the main thing, there's two modes. There's a command mode and the edit mode. The command mode sort of deletes cells, moves up and down, chooses which cells to run. Then if you're actually typing within the cell, you click Enter on it and you enter the edit mode. But so I'll let you guys sort of peek at that, and I'll kind of mention some of these as I'm using them. All right, so that gets us to pretty much expert hacking, but all right, so moving on to pandas. Okay. Well, actually, let me just mention the 3 or 4 things I'm generally going to be talking about. Pandas will be kind of next. So within pandas, there's this data frame, which is sort of most useful. Pandas can be kind of tricky, and it's like sometimes it literally is like that. But the more you get used to it, the better life becomes. And then matplotlib is the plotting library, which everybody hates, but it's sort of the standard, so we all use it. Then we'll go through like a regression example and a classification example. And I'll just say here maybe that this kind of like statistical learning sort of umbrella, I think, includes the machine learning community, which is kind of like prediction heavy. And then I'm tempted to say ours, judging by the hands earlier, but maybe that's not true. And kind of the social science community, which I think is like really the understanding heavy, maybe at the cost of not maybe at the cost of prediction. So as we go through the regression and classification examples, we'll see how these emphases manifest themselves in the actual work that people do. And I guess now we are just about ready to roll. Right after we get past this awkward wondering. All right, so pandas. So at this point, I guess you can start typing in, what I have. So am I correct? Like you guys have a blank open notebook or IPython notebook on your computers, and you're waiting to type stuff in. Is that because I don't know if people. All right, so with Python, and again, how many people have used Python before? That's almost okay. So pretty much everybody. All right. Great. All right. So we're gonna import this package pandas. Okay. What it's gonna give us is especially this data frame structure, which is kind of like the R data. It's kind of built like the R data frame structure. So a few years ago, when I had to choose which language to really invest in, it was basically R or Python. and it was like, I didn't like that with R, like the assignment thing was like kind of nasty looking, like you had to do the arrow thing. So I was like, all right, I guess I'll do Python. I mean, it's whatever, it's all the same. I think at this point, especially with Pandas, it's now become like R, and I feel more. So now I feel validated, like the right choice was made. The thing that dataframes let you do primarily is make matrices with data type, with heterogeneous data. So you can have like strings and numbers and all these things in the same structure. You couldn't do that before in Python, not easily anyway. So now it's like super easy. And also to access things within this data frame, you can now you not only can specify specific indices, but you can also specify the labels. And that we'll see is what makes this like super awesome for data wrangling. So for example, let's load in a data set. So I'll give you guys a second to get this address. Hopefully this works for everyone. So the data frame, df for data frame. So to take a peek at it, we use the head command. And this prints the first, I think, 5 lines. All right, so now we got this data set. We're going to try to get acquainted with it. So we look inside. All right, what do we have? So it's automobile information. We got horsepower. All the column names at the top. Let's kind of get at some of the metadata. So we'll run this cell here, and we'll take a look at the shape of this thing. So we know there are 397 rows, so vehicles. Yeah, of course. Yep. So to access the columns, you can just do it df.columns, really easy. The index is basically the labels that go on the rows, okay? That's your vertical axis. To access that, you just type in df.index, and there's a whole bunch of them, so I'll only take a look at the first 10. Right, everybody got the link? All right, so so this tells us the shape, the sorts of columns that are in this data set, and what's in the index, which at this point is just numbers. Okay, that looks about right. All right, so usually after that, there comes a step when you kind of customize your data frame to be accessed the way that you want it. So it feels to me like you're getting it like nice and cozy, like where it's, So for example, let's say instead of the index being just a number, which is sort of probably useless, let's make the index the name of the car, because that's sort of how that intuitively makes sense, right? It's like this car has the following attributes. So we can just access the index like so, and this says basically take the column of names and assign it to the index. After that, I'm going to delete the column of names because now we have it in the index, and look at my data frame again. And what we see now is that the labels, the index is now the car names. All right, this to me seems cool. This makes sense. All right, so now let's access different parts of this, and also I shouldn't actually pay close attention to the time because I feel like I'm going to run over. Okay, so you can access stuff the dot way or the bracket way. For example, I'm going to define a column, miles per gallon. I'll define a column weight. Pandas and NumPy, which is what it's built on top of, is really smart. So you just like say divide and it knows exactly what to do. It's going to do it element wise. Okay, and that's going to split. So now I'm going to take a look at the results. I am giving Pandas a list of columns I want to display and taking the first 5. All right, any questions so far? We're so good? Okay. So let's say, here's where it gets fun. Okay. I do, so I'll give the link later. Because otherwise everyone's just gonna like download it and like not pay attention to me, so it should be sad. Anyway, let's sort of play with getting different subsets of the data. Let's say we want all Fords, okay? Oh, okay. Bill, do you mind taking a look?
Yeah.
Does it just not downloading or something? Or? All right, you guys figure it out. Okay, so let's say we want to take all the Fords. What would that entail? Well, we, for example, could do it this way. We could go through all the, our index is now the car names. It's a list. I'm gonna go through elements in this list. Sorry. And if Ford is in the name, that's going to be true. If it's not, it's going to be false. So this creates 863 or whatever, how many rows there are, a list of trues and falses, right? That list then goes into the brackets of my data frame, and the result will be only those rows where it's true. Okay, makes sense. The cool thing to note here is that the brackets can be used to access columns and rows. And here Pandas is really smart, so it figured out that like, oh, hey, he's giving me like 860 things. He probably wants the rows. Because at no point did I specify, oh, this refers to the rows or columns. So that's really cool. All right. A lot of the Angry Panda GIF above comes down to like learning the dark art of like indexing stuff. Like it seems like it should be really simple, but it's often not. So you can index, like get access things by label. You can access things by location. This is kind of like the usual way, and by both. So here, for example, I'm going to take the weight and miles per gallon columns and only the first 5 rows. And Pandas theoretically should spit out that. And actually, what happened to our index? Wait a minute. And then this, well, okay. So somehow our index disappeared. To think about why that happened, but yeah, but this is a good example. So that's something doesn't look right to me. I thought these would be the names, but whatever. Another really useful function is value counts. So if we want to see what kind of years are in this data, we'll access that column and we'll do value counts on it, and it'll show us years. So I think the pizza here is here, so I'm gonna kind of rush through this a little bit. Basically, another example is, all right, let's say that's another example of how awesome Pandas is. Say you want to change the 70 and 71 and stuff like that we have in the year to an actual legitimate number. Well, there's this thing called apply. So you pull up the column that you want, which is the year, and you apply a function to it. Lambda functions are sort of like in-place functions that you don't have to define separately. And it says, given x, convert it to a string and add 19 before it. And boom, now we just went in like half a line, basically. We went from, 70, 71 to this like nicely formatted thing. All right. Let's say we want to change it back now. Okay, so we finished doing that. I'm now gonna assign the result to year. So year is gonna become the full number. But let's say I want the original thing back. I only want the 2 last digits. Well, that turns out to be a one-liner too. I'm going to convert year to a string and take the last 2 letters, basically. So, and that spits out what we had before. So that's an example of like something that may have been really annoying in the past. Like you have to write a for loop and like blah, blah, blah. Here it's like just one line, like boom, boom, boom. Lastly, visualization. So matplotlib is like the thing, quote unquote, everybody uses. But as I was actually prepping for this, I'm realizing that's becoming less and less the case. But it's this really annoying like MATLAB style plotting library. There's others. This one I think just appeared in Python. This one I'm starting to use more and more. some kind of common kinds of things we might want to do with matplotlib is get the histogram of something. So I'm going to import it with this command here. Scatter plot or plot, which with plot you can do a whole bunch of different things. So for example, I want to grab a histogram of the weight, like I'm trying to get acquainted with my data. All right. Well, that's as simple as, you know, pulling up our weight column and putting it into histogram. This doesn't look very pretty because it's like very bare bones. So maybe we want to add like a title, or we want to add an X label. You know, these are like some common things people tweak with the figures. What's really cool though is that Pandas now includes sort of built-in plotting things that make it yet easier to do this stuff. So, for example, the same thing I did earlier, I can just do as a Pandas command, like this hist is now a method of the weight series, you know, which is like super shorthand, super convenient, very quick. I'm now gonna sort of prettify my graph a bit and get the following. All right. Similarly for scatter plots, now this is failing. Oh, so maybe it's because I converted year to strings. Now it doesn't know earlier. Now it doesn't know what to do with it. Let me try one thing. If this works, okay. So here's a scatter plot. Okay, very easy, very quick, super nice. Box plots, another example. This is pretty cool. It gives you the median and the interquartile ranges, I believe. And you know, there's like all these different kinds of graphs you could do. Here's an example of where I'm going to take 3 columns and look at the scatter plots between all of them and the distributions all in like 2 lines. You know, A+. But wait, there's more. And this will be the last thing. So what is this XKCD business? That looks familiar. Wait a minute. What is going on here? My mind is literally going to explode. Oh my God. I can now plot things with XKCD style. It's amazing. That's when you want to like spruce up your, you know, whatever workshop presentation, you can throw that in. And so that'll be the first notebook. Next, we're going to move to regression. And now let's get some pizza. All right, so now that we all have greasy fingers, it's time to return to the keyboards. So I'm pulling up the second of 3 notebooks. So this is the regression example. And I'm now realizing a lot of people have probably done regression stuff before, right? So raise your hand if you have. So that's pretty much everybody. So I'll just, I guess, kind of mention the package that, you know, is used in Python often for this sort of thing, and kind of quickly go through. So regression, we talk about usually predicting continuous outcomes, or predicting or explaining. Depends on your view. Classification, which will be kind of next topic, is what I think we social scientists aren't as used to, and that's kind of what a lot of machine learning is about. The goal with kind of the usual regression situation is you got some kind of continuous outcome, you're trying to explain it best or predict it best. So you might have, let's say, if you only have one predictor, let's say year, and the blue data points is your raw data, you're trying to find the line that sort of fits the data best, which usually comes down to minimizing the squared distances, these EIs that I show here. And there's variations on what sorts of things you want to minimize, but this is kind of the standard thing I think everybody sees. So how do you evaluate how well you did? Usually you would use this thing called R-squared, and that's a measure. I found this chart and I was staring at it. It makes sense, but I don't know if it's like more harmful than helpful. But after staring at it for like 5 minutes, I was like, yes, this makes sense, but it took 5 minutes. But basically, so R-squared measures how much your data deviates from the line. So this is like the blue square in here, for example. We drew a line and the deviation is this much. So we square that and we get the square. And then we sum up all our deviations and we compare them to the total deviations of the data about its mean. So in this case, this is for this point, this would be the big red square. And the idea is that, the closer your line is to the actual points, the smaller those squares will be. And that would mean, hey, like you are actually explaining how the data came to be. You're approximating how the data was generated, you've explained it. And so the way to capture this quantitatively is with this R-squared metric. So coefficients, so social scientists, I keep sort of harping that distinction, maybe even more than I should, but it's just noticeable that we worry about this thing a lot. In the machine learning literature, seems like not as much. So, we care about like big coefficients, big effects. We then want to say, well, are these statistically significant? Are these important? Is this just kind of by chance? And we kind of do that by saying, well, all right, if there was no effect, what would be the distribution that we would observe? And then here's how big our actual coefficient is. Oh, wait, that looks really unlikely to have come from sort of the null model. So it's kind of inconsistent with the null model. It's kind of like not exactly what we want, because what we really want to do is be able to say like, hey, we observed this coefficient, therefore the model is blank. Here's our confidence in it. But instead we're saying, well, if the model is the 0, where there is no effect, we would observe X, Y, and Z. So it's not quite what we want, but that's in practice what people do. And then if the evidence is especially inconsistent with the kind of the null model, like if the probability is below 0.05, then we say that, hey, this coefficient probably didn't come from a population where there's no effect. All right, so now we're going to import a bunch of things. And by the way, I can't really gauge if I'm going like too quickly or slowly. So if you're like vigorously typing, but and I'm like vigorously scrolling, type like maybe even more vigorously so I can like sort of see it, and be like, whoa, I need to slow down. Okay, so we'll do kind of one quick example. These are the same libraries that we usually use. This might be a new one, stats models. So for regressions, I think that's kind of the go-to, and it's prints like the most convenient, summary statistics and stuff. This API is the part of stats models that we're going to use. I'm going to call this whole thing SMF. Okay. All right, so we're going to pull up our data. Will be housing prices in Boston. That'll be just like something for us to play with. In fact, like we don't know the people in Boston very well, so let's do they care about pollution or not, and how much? Maybe that'll be like our sort of motivating question. So what we're gonna do, sklearn, scikit-learn comes with a few built-in data sets. So if I run this cell, it should work. Hopefully the same for all of you. So is everybody to this point? Everyone's got the Boston stuff loaded. Is anybody failing? Is something failing along the way? I guess I shouldn't have said it. Is anybody failing? Is any, are there any problems people are running into? Okay, we're good. Okay, so this Boston data structure, I don't even know what it is. My first instinct is like, let's get it into Pandas as quickly as possible, because whatever it is, like I don't want to know. Pandas, I understand. All right, so but there's this description string, and so this will tell us where the data set comes from. I think it's like 1978, or that's when the article was published, but I forget exactly when the housing prices are from. These are the variables in it, but we're gonna look at those in a second anyway. And this will be sort of the actual the price of the houses. That'll be our dependent variable. So if you run the following, oh sorry, you got it. All right. Okay, moving on. Okay, so now we're gonna like set up our data frame in the way that we find most useful. So the Boston data comes in it's an array in this data field. I'm gonna create a data frame using that data, but I'm gonna specify my own column names because here it doesn't have column names. So I create, the list of variables. This is same as were given to us above. And I guess I'll leave this up for a bit in case anybody wants to actually use those column names. And then I'll also now add my dependent variable, which is the target variable, and that'll be the median value. All right, so I'm gonna run this, hope for the best. Okay, it works. Just to make sure, these should now be the column names. I will take a look at my data frame.columns, and it comes out to exactly what I want. Okay, that's good. All right, so moving on. Let's say I'm gonna take a variable just to play with. Let's say crime. I'm gonna do a quick scatter plot. Crime versus median value. All right, that comes out like so. And this is kind of to demonstrate the sort of convenient everyday kinds of features of Pandas people use. This looks to me kind of weird. Like, why are there all these zeros? The data frame, the data description said there are no missing values, but then there's like all these zeros. What's going on? Well, okay, let me take a closer look at the crime variable and do a histogram of it with a whole bunch of bins. Looks like there are a bunch of values. I could, maybe do what? I could say, let me take a look. Like, basically, I'm trying to figure out, are these all zeros? Because that shouldn't happen, right? Like, are there situations where the value of crime is 0? All right, so I'm going to make an array of trues and falses. And it's telling me it looks like it's mostly falses. Okay, so in fact, these aren't zeros. These are just like really small numbers. Okay, that makes me happy. All right, so probably there isn't like some kind of data entering error. So I'm going to delete this column now because I don't want it polluting my. All right, so now that I've sort of seen, all right, those are probably legitimately small numbers. All right, I'm gonna try to do a quick regression. The stats model .formula API is now SMF and has this OOS method. And for you people, for you users of R, this will look really familiar. This is sort of the R style formulas that Python now has too. So it's really, this should like put a lot of smiles on people's faces. So it's like, all right, here's less stuff I have to learn. So here I'm just saying, the median value will be regressed on the crime variable, and this says don't use intercept. And then I'm going to fit. And after that, I'm going to print the summary. And these are almost like platform independence. I think, a lot of us are like used to staring at these like boring tables. So can someone, who's kind of used to looking at these regression tables, like say something about what we found out about the crime variable and its effect on price? Is everybody too? All right, I'm gonna start calling on people, and by people I mean Bill. Okay, so we're looking at you're looking at the p-value here, and it's really low. Okay. And then it's positive, right? So it's the more crime, the higher the price, is what we're finding out, right? Which is weird, right? Like, is weird, and in fact, very weird. In fact, if we plot that same scatter plot above and put the regression line there, which is done with the plot command. So yeah, as I'm looking at it, there's a lot of like random Python-y things that I probably don't have time to explain. But if ask maybe later or. So this looks weird, doesn't make sense. Well, that's because maybe it's because we didn't add an intercept, and so we were sort of forcing the line to go through the 0. All right, so now we're going to add the intercept, which here is done automatically. It's only to get rid of it that you would do this, but the intercept is there by default. We're going to do this exercise again, and then now, and I've learned my lesson. I'm not going to ask people to interpret regression coefficients because apparently nobody wants to do that. So now we find that, hey, the more crime, the lower the value. All right, that makes sense. Our squared earlier was pretty dang low. Now it looks a lot better. All right, so we're moving in the right direction and getting better at predicting. So if we draw the line again, we find that it looks more reasonable, but not quite, right? Like, as a matter of fact, like a linear sort of approach might not work here. We might, maybe an x squared or like a negative x squared type of thing would work. That's something sort of to play with. The categorical variable and standardizing are sort of two common things we do. So that's to make the so for standardizing, it's to make the coefficients more interpretable. If you got different units and you want to compare coefficients, then it doesn't make much sense to say, well, like, if crime is measured in, instances per 10,000, but, nitric or whatever the chemical is measured in like 0.001 per whatever million, our coefficients aren't comparable. But if we standardize them, divide them by their standard deviation, then we can talk about standard kind of metric. Well, if one deviation increase in oxide gas or whatever has a greater effect than the one standard deviation increase in crime, which again isn't actually very comparable, but we're getting closer to it. So all this kind of stuff is done by very simply amending your formula, which, for example, here, if I want to make crime a categorical variable, I could do the following. I just put it and see if I want to standardize stuff, I can do like so. So maybe this will work, maybe it won't. So crime might have too many categories now, or my computer might be too slow. All right, I'll let it run. So yeah, I'm guessing crime. So this ended up creating too many categories. In any case, all right, so I'll stop with regression there because I think like most of us are sort of familiar with it. Stats model is the module people use. And I'll now move to the classification example. All right, so here we're going to try to detect, given a string, we'll try to detect the language it comes from. The big topic, I think, with classification is overfitting. That's something that in social science just like rarely comes up. So it's in part because we use very simple models like linear regression. It's like very robust to overfitting. It's hard to make a line be very sensitive to the idiosyncrasies of your data. But in machine learning, that's like at least to me, feels like the huge distinction. That's like what everybody worries about. And so the overfitting issue is basically, the sort of illustrated here. So the data has some noise naturally, and if you allow your model to be too flexible, if instead of a line like on this left panel, we introduce a whole bunch of parameters and make it like an nth order polynomial, that polynomial can capture the idiosyncrasies of the data really well. But as we can kind of intuitively understand, like, well, that doesn't mean we understand it better, right? It's just like if we use the same line on other data, it's actually going to do worse than this kind of medium solution, which is sort of like follows the data but not super closely, because again, there's just a lot of randomness in there, and we should take account for it. So, so machine learning, like kind of computer science people, worry about this a lot, and so the solution that, again, like I didn't mention it in the regression thing, we never really hear about, but the solution they use is they routinely, I mean, pretty much always split their data into two sets. They have the the training set, and then part of it they reserve for validation. And that's kind of, I think, in part because they really worry about the prediction, like how well am I predicting? To us, it's often less of a concern, and so we don't do this as often. But any kind of computer science paper, you'll like, it'll be funny if you don't do this. Whereas, like, I think for sociologists, it'll be almost funny if you do. Kind of weird. But anyway, so what people do is they reserve a set for their sort of training, and that's the actual metric that will be used. So you get now, because we have the split, we get two sets of sort of outcomes. We get the accuracy and the error on the training part, nobody cares about. And then the test set, that's the only one that actually matters. Is this kind of a familiar topic to some extent to people? So, okay, so if not before, then now to some extent been broached. Okay, so again, we're going to import some stuff, the usual suspects. So if you do Shift Enter, that'll run the cell and move you to the next one. It's convenient. So this this is old. Erase. Okay, so the data description. So this is a data set I found, which I think will be nice for us. So if you guys could go to the zip and extract the text file. So I already have it, but just checking to make sure the link works. So inside of there's a text file. There are, I guess, 21,000 rows in that text file, 21 different languages of the countries that are in the European Parliament. And this is from, I think, 2011, but I forget. Oh, yeah, sorry. Yeah. So I'll leave this here for a sec. Take a drink. So while people are downloading stuff, are there any questions that are coming up? Either really good or really bad. I have no idea.
There's going to be plenty of time after this notebook too.
Yeah. So as I'm checking the clock, yeah. So I think like the idea was that we'd spend about an hour just kind of going through these tools, and then you guys would hack for an hour. So that might be the second part of that. Might be more like 45 minutes or something. But hopefully decent chunk of time. And then as you guys do that, Bill and I and Nathan, when he gets here, will kind of float around and help out however we can. So, and then you'll want to place the text file in the same folder where your notebook is. Is that working for everybody? File's fine, everything's in there? Yep, you got it. All right. Everybody got it? Okay, so I'm moving on. All right. So, okay, we now want to read in this file. It's a lot of different languages, so we can't use the sort of standard ASCII encoding. This set of commands work for me. So UTF-8 is one of the Unicode character sets. We import this codex module. We give it the file name. We want R's for reading, and then we'll read all the lines in this text file and make a list of those. That's what lines is going to end up being, a list of the sentences. All right, and then
Sorry, would this be a
Yeah. So inside of the zip should be text file. All right. Oh, okay. Sorry. Yeah. So that must be it. What else is in there?
That was all.
That's the only thing. Okay. So that must be it. Okay. Okay. So now lines. I'm gonna take a quick look at lines. Yeah. Sorry. So lines is this huge list of Unicode characters. That's what it's supposed to be. This splits the strings on tab, and because there's like the strings are formatted as like language and then the sentence. I'm gonna put this list of lists into a data frame. Pandas is really smart. It's gonna know exactly what to do with it. It's gonna make it, 221,000 by 2 table, and I'm gonna specify the column names. And I'm gonna look at what results, and it looks pretty good. Okay, it looks. I don't know what the story is with these like prefixes because they're different from the language, but I actually suspect it's maybe like who the speaker is addressing, perhaps, or I don't know. All right, so that looks good. Everybody there? Okay. So again, this value counts function. All right, what kind of languages do we have in there? Well, let's take a look. We got 21 of them, 1,000 sentences each. Okay, so good. So far, so good. All right. How do I take a look at a specific language? I can do it with this slicing notation again. I take the language column, I look where it's equal to English, and then I put that array, this ends up being an array of trues and falses. I put that into the original data frame and look at the first 5 rows. Okay. There's similar kind of subsetting thing. There's this function called isIn. So I'm gonna, for kicks, try to classify between LT and LV. I think, and you guys probably know better than I, but I'm guessing Latvia and Lithuania, I hope. But, tell me if I'm wrong. So I'm going to create this sub data frame, which only has the Lithuania and the Latvia sentences. All right. Okay, so now we're going to build our classifier. We're going to use the logistic classifier. As I'm talking, I realized I had a figure that I guess I erased. Wow. That was sort of like visualizing how that worked. The logistic regression thing. Basically, it's often used for predicting binary outcomes, like if it's a 0 or 1. It's very similar to the kind of linear regression, except we're wrapping the outcome in this logistic function. And instead of a line, I'm literally waving my hands, we're getting this, the output is constrained to be between 0 and 1, which is what we want. So it's basically predicting the probability that something is in either 0 or 1 in class Lithuania or Latvia. So now what features do we want to use to predict? So let's say we just do the simplest thing. We count the number of words, or we use, in this case, the top 50 most common words as our features. So if so the variables that social scientists speak of in machine learning parlance are like features, like feature engineering. So our predictors will be a row of 50 things. Oh wow, so that is dumb, and I need, totally forgot about that. So it should be at my desk. Thanks. I'm gonna turn down my brightness. So from this line, so scikit-learn, which is a function, sklearn, which is a sort of package we're using for this machine learning stuff, has a bunch of very neat, handy functions. It really pays to kind of learn them all if you're going to be doing this. So count vectors, there's one of them. We tell it the number of features we want. Going to use the top 50 words. and each sentence now has 50 variables attached to it. I am now, first I define this thing, then I actually give it the data, which in this case will be the text of the actual sentences. This fit transform is going to spit out the matrix of features. I'm going to run this. And I'm going to take a look at its shape. This X features is what we're actually going to be using to predict. It's a matrix, and it has 2,000 rows for the two languages and 50 features. Okay, that's exactly what we wanted. All right, so now we're going to do the thing that I think is maybe a little bit unusual to the more social sciencey people. So we're going to split our data into two. There's, again, a handy package for that. It's called train, or handy function train test split. We give it our features. We give it our outcome variable that we're trying to predict. We give the size of the test set, which will be 0.2, 20%. And we give it, and this thing doesn't matter for us. And then that spits out four things. The X train, X test. That's for our features, and this is for our outcomes. So let me run that. Thanks. Yeah. Low brightness. Okay. All right. So is everybody? Am I slowing down too much now? Is everybody here? Okay. So I'm gonna do that. I'm gonna look at the composition. Okay. So this is our test set and has 188 LT sentences, 212 LV sentences. So your numbers might be a little bit different. But so we split our data. Okay, that stuff is good. We're going to train our model, which means fitting our logistic regression. So we do that. So note, this is only using the training data. At no point have we touched the test. So now we evaluate, and this is kind of a big topic. Again, I think like much bigger in machine learning than for social science. Like for us, it's like our squared coefficients. I don't think anybody looks at much else. In the kind of machine learning world, there's like all sorts of outcomes you might care about. So accuracy is probably like, the easiest. That's the most sort of intuitive. People also worry about maybe precision and recall. So if there's sort of one kind of class that's especially valuable. So let's say you're working at Visa and you're trying to predict like fraudulent transactions. Like you don't really care about finding the non-fraudulent thing really well, because that's hopefully most of them, and like that doesn't help you at all, right? So your really only goal is to see how well you're going to be able to find the fraudulent, the 0.001% of fraudulent things. So in that case, you'll worry about precision recall. And then there's like a bewildering array of like other metrics that people use. But all right, so we're going to use this predict. So CLF is our classifier. It has this predict function. I'm going to give it the features from our test set. It's going to put the predictions into this array. And now I'm going to look at a handful of metrics and how well we did. So I'm going to run this. Okay. So accurate. And so again, just to emphasize maybe too much, like at no point did we touch the Y subtest, which is where our correct answers are, right? So this is just really just predicting. So for accuracy, there's this metrics module, which has a bunch of these sort of common things. For accuracy is super high. Precision recall, just this classification report function, really amazingly nice. The confusion matrix is how many things you classify correctly versus incorrectly. And so here we see that if something is a zero, which in our case would be whichever like country came first, LT or one of those, we're getting most of these correct, but then we are calling some zeros ones. And I always forget whether it's the true predicted comes at the top, or I always switch those up. But evidently this is the bad square. That's where we're kind of messing up a bit. but overall, like really nice. Okay. Out of curiosity though, so again, this is like only on the test set. How well did we do on the training set? And apparently we did, I mean, just barely worse, maybe really about the same. All right, so we're apparently not overfitting much, which is maybe not super surprising because we're only using like 50 features, and we have like 2,000 items. All right. So ROC curve is another sort of like potentially not. So who's kind of heard of ROC curves? So that's another thing that like sort of seems like maybe the most preferable like metric by which to evaluate classifiers. So on the x-axis we put it's kind of captures like the sort of the cost you pay for the performance. So I'm just gonna graph this and sort of talk through it. Except I am failing somewhere. Oh, right. So, okay. I guess I forgot to. These are now CLS. F. Okay. So that's a really unusual looking ROC curve because generally speaking, it's like so. And the more you are to that corner, the better the performance. But here we set up our example like an especially easy one, it turns out, because apparently it's very easy to predict language using these features at least. But so on the bottom sort of goes the cost, and on the top goes the kind of the benefit. And the idea is pretty simple. Like the more sort of cost you incur, the more benefit you incur. And the question is, what's that trade-off? And this shows us that generally it's for this classifier, it's really nice. For sort of the one like number, it's the area under this curve. That's the number that usually gets tossed around. Like, whoa, what's the AUC, area under curve? That's kind of like the way people evaluate. Lastly, we might want to take a look at the actual coefficients that made the difference. So I'm going to pull up from this, from our logistic classifier, I'll pull up this coef thing. I'll get the first element of that. Sorry. I'll put it together with the feature names, put it all into a data frame, and then sort it according to the value of the coefficient. And let's see what we get. So we get something like so. So these are the odds that you are of class 1 if you have this word. So apparently if you have this word, you're really likely to be a 0. And going to the top coefficients now, it's like if you have this word, then you're almost certainly in the 1 class. Okay, so this was, I mean, that about wraps it up. For people who are kind of looking to exercise and push, one, I think, useful exercise to do would be to get a classifier that, I mean, here I sort of cherry picked like 2 languages, which is sort of a nice, silly kind of thing to do. Let's build a classifier that, given any of those sentences, spits out any of the 21 outcomes. Like that would be nice, right? Like that, in practice, maybe the sort of thing one would want to do. And so the usual thing, which is like this, it feels a little bit patronizing, but like but anyway, the usual thing that the way that's done is you build 21 classifiers, each of which classifies one versus all. So you take a language, is it Latvian or any of the others? Is it English or any of the others? And then you see which of these classifiers, given a sentence, gives you the highest probability for being that specific language and not all of the others. And that's the prediction for the language for your sentence.
That's sort of an unrelated question. I'm not related. So use scikit-learn to extract features automatically. And it looks like it's using whether or not it contains a certain. Is there a way like change that setting?
Yeah, so this is like the most naive of the things you can do. So I mean, if I uncomment this line, it's gonna use characters.
Oh, okay.
So yeah, I mean, good question. A smarter thing to do would be to actually use the features above, which sort of weight them according to how frequently they appear. And these are, and then, yeah, I mean, luckily this seems to work now, but usually like feature generation engineering is like a big thing. Like you got to find features that actually make sense. But here we're it's an easy enough problem. All right, so I'm gonna stop there. Are there any, and I guess now we're gonna enter the kind of interactive like hacking time. Are there any other questions while I'm up here? Cool. All right. Thanks.
Hey Misha, where can we find these notebooks?
Oh, well, why, Eamon? Thanks so much for your question. So all this is on my GitHub. So if you go here, so all this and more, and the more is garbage, but I haven't gotten around to like erasing it. So if you go to this folder on my GitHub, you'll see the 3 notebooks I used today. But among them are these other things. And when you hover over them, you'll see that they have like weird extensions like .ipy, bc, blah, blah, whatever. So those you don't want. You just want the ones with legitimate extensions like this one, for example. Awesome. So now, yeah, let's get out our own data and play with it. Thanks.